Okay, let's dive into this explainer. Ever since scientists first wrapped their heads around Coulomb's law, that fundamental rule dictating the force between two charges, there's been this massive, almost philosophical mystery hanging in the air. We knew for a fact that a charge Q could push or pull another charge from a distance, but the really profound question was, how? I mean, literally, how do two objects interact when they aren't even touching? It's like a giant puzzle. So let's follow the clues that those early scientists used to crack this case wide open. To really appreciate this mystery, imagine we've got a single point charge just sitting there in a total vacuum. We place a second charge nearby, and boom, instantly a force acts on it. But now suppose we pluck that second charge right back out. What exactly is left in that surrounding space? Is there just nothing? A totally empty void? Because if that space is truly empty, if there is absolutely nothing there, then how on earth does a force magically know to act the very instant we drop a new charge back into that spot? Action at a distance without any physical connection? Yeah, that just didn't sit right with physicists. To answer this, they realized they needed a totally new concept. The radical idea that the first charge actually alters the very fabric of the space around it, creating this invisible environment everywhere in its vicinity. Now, what's really interesting about this setup is how we actually map out that invisible environment. We've got two distinct players here. First, there's the main source charge, we'll call it capital Q, and then there's the test charge, lowercase q. The source charge is the main event, right? It's sitting there anchored in its original location, actively churning out this field. But to figure out what that field actually looks like, we have to bring in our test charge. And here's the catch. For our measurement to actually work, Q must be infinitesimally small. It has to be so tiny that it doesn't exert its own force back onto Q and totally ruin the whole measurement. We often just assume Q is anchored in place by some outside force, just so we can accurately measure the space around it without things moving around. So if we look at the math, the electric field is essentially the force a unit positive charge experiences at a specific point. We define it simply as E equals F divided by Q. So the crucial point is that once we divide out that test charge, the resulting field E is completely independent of it. Think about that for a second. This field exists everywhere. It is literally at every single point in three-dimensional space, perfectly mapping the electrical environment, totally regardless of whether our tiny test charge is actually sitting there to feel it or not. Let's visualize what this field actually looks like out there around our source. It's not just some random, chaotic cloud. It has incredibly precise geometric traits. For a positive source charge, the electric field acts almost like rays of sunlight, pointing radially outwards in every single direction. Now, if the source charge is negative, all those field vectors flip and point radially inwards. And since the force between charges depends exclusively on the distance between them, what we usually call r, the magnitude of the electric field also depends only on that distance r. What does that mean? Well, if you draw an imaginary sphere around the source charge, the strength of the electric field is exactly the same everywhere on the surface of that sphere. It possesses this perfect, elegant spherical symmetry. It truly is an invisible, mathematical web extending infinitely into space. But, the universe is rarely as simple as a single, isolated point charge. Things get messy. So, when things get more complicated, we rely on the superposition principle. Let's move on and see how this builds. To find the total electric field at any specific point in space, we just follow two very logical steps. First, we imagine our unit test charge sitting at that point, and we calculate the individual electric field created by every single source charge in the whole system, one by one, completely ignoring all the others. Second, because force is a vector, meaning it has both strength and a specific direction, we just add all those individual field vectors together. That combined vector sum gives us the exact total electric field at that specific location. It's brilliant, really. Complex environments are just the elegant sum of their individual parts. Now, it is totally fair to play the skeptic right here. You might be wondering, why go through the trouble of introducing this intermediate quantity called dielectric field at all? I mean, the only thing we can ever actually measure in a physical lab is the literal force pushing or pulling on a charge, and we already have Coulomb's law and the superposition principle to calculate that force directly, right? So isn't inventing this invisible field existing in empty space just an unnecessary middleman? Is it all just a fancy, albeit elegant mathematical trick? Well, the honest answer is that as long as we're only talking about stationary charges, the stuff we call electrostatics, the electric field is incredibly convenient, but honestly, not strictly necessary. It acts as a beautifully elegant way to characterize the electrical environment. It lets us map out the potential forces in a room without having to know what specific test charge might eventually walk into it. It's a fantastic characteristic of the system itself. But if we stopped there, it would indeed just be a clever mathematical construct. The true physical significance of the electric field, the real aha moment, only emerges when we push beyond stationary charges and enter the dynamic, constantly changing world of time-dependent electromagnetic phenomena. This dynamic world introduces an absolute, unavoidable cosmic limit, the speed of light. Imagine we have two distant charges. Suddenly, charge 1 accelerates and zips over to a new location. We know from the laws of physics that the absolute greatest speed any signal or information can travel through the universe is c, the speed of light. Because of this absolute cosmic speed limit, the effect of charge 1's movement cannot instantly reach charge 2. Instant action at a distance? Impossible. Instead, there is a distinct, measurable time delay. And this brilliantly illustrates the core issue. At time 1, charge 1 moves. At time 2, that movement creates a ripple, an electromagnetic wave that propagates across that supposedly empty space at the speed of light. And finally, at time 3, that ripple reaches charge 2, and only then does charge 2 actually feel a change in force. This unavoidable time delay? It completely changes everything. It perfectly proves the true, undeniable physical reality of fields. Think about it. During that time delay, while the signal is literally traveling between the two charges at the speed of light, where is the force? Where is the energy? It's right there in the fields. The field elegantly accounts for that delay. Because of this, fields are not merely mathematical constructs or theoretical mapping tools. No way. They are very real, tangible physical entities. They have their own independent dynamics. They evolve according to their own specific physical laws. And most incredibly, they transport energy through space. If you turn on a source of electromagnetic fields for just a tiny fraction of a second and then completely switch it off, the source is gone, but the field it created, it will just keep propagating through space, carrying energy with it completely independently. We really owe this profound realization to the brilliant Michael Faraday. When he first introduced the concept of the field, it totally revolutionized our understanding of the universe. He looked at magnets and charges and envisioned these invisible lines of force permeating the space all around them. What started out as just a way to visualize forces, and what seemed like an optional mathematical convenience for stationary charges, was ultimately revealed by Faraday and the scientists who followed him to be the fundamental fabric of physical reality. Today, the field is absolutely, without a doubt, among the most central and important concepts in all of physics. So our journey today reveals a universe that is far more complex and deeply interconnected than just a simple, empty void. We started this explainer by asking how forces travel across space, if what we call a completely empty vacuum can actually hold real, evolving physical fields, entities that follow their own rules, ripple at the speed of light, and transport actual energy from one side of the galaxy to the exact opposite side. We really have to ask ourselves, is space ever truly empty? It turns out, the space between things is just as physically rich and important as the things themselves. Keep that in mind the next time you look up at the vast, seemingly empty expanse of the night sky.